Hi there, my name is Aaron Lanterman. I'm a professor of electrical and computer engineering at Georgia Tech. Before closing out this series of videos for ECE2026, Introduction to Signal Processing, focusing on finite impulse response filters, I wanted to take a look at some examples of filters applied to images. We generally characterize filters as having low-pass, high-pass, or bandpass characteristics. In the context of image processing, low-pass filters blur images, whereas high-pass filters detect edges, and are often used in image sharpening algorithms. We focused on filtering one-dimensional signals, so to start with, let's consider taking just this row from the scan of a homework assignment, where we're going to represent black as being a high value of 255 and white as being 0. So this is that row presented as a one-dimensional signal. If we apply an 11-point averager that's a non-causal filter, so you can think about the impulse responses actually being centered at the origin, what we see in the dashed dotted line is the original signal, and what you see in the solid line is that signal blurred by an 11-point averager. Now, if we apply that operation to all the rows, and then apply that same operation to all the columns, we get this blurred image. This is an example of a two-dimensional separable filter, because we can decompose it as this convolution along the rows and then a convolution along the columns. There is a more general concept of two-dimensional convolution where you can have impulse responses that are not separable like that. In the context of image processing, impulse responses are often referred to as point spread functions. The equivalent of time invariance in image processing is spatial invariance. The Hubble Space Telescope is interesting in that its fundamental imaging process may be viewed as a linear system, but it is not spatially invariant. Here we see some example observed and mathematically modeled point spread functions for the Hubble. And if we scroll down in this paper a little bit more, you can see these two different point spread functions associated with different locations on the image. The varying aspect of it comes from the fact that the telescope has this mirror assembly with these various supports holding it into place, and the obscuration that creates changes depending on the angle you're looking into the camera at. In addition to this magnitude, there's also a phase function associated with the way the mirrors are shaped, and you can use a fast Fourier transform to compute the point spread function. We'll look at discrete Fourier transforms later. Here in the image on the left, we've added a sinusoid to each of the rows. Now, adding that sinusoid may make the pixel values go negative, and we're displaying any negative values as white. If you apply that 11-point averager, basically the upward going parts of the sinusoid cancel with the downward going parts, so that sinusoidal interference has been removed, but there is this possibly undesired effect of the image getting blurred.